It's my pleasure to welcome Yang Chai from McGill University. Um, Yang has been an intern here a few years back, so it's good to have him back. And he's going to talk about some new results in mechanism design. So,
Thanks for the nice introduction. So I'm Yang. Today I want to talk about a new framework based on duality that you can use to design simple mechanisms. So the talk is based on two papers. One was Nikhil, Matt Weinberg, and the other one was my student Mingfei. Okay. So although the framework can be used to essentially handle any mechanism design settings, I'm going to focus on revenue maximization for today. And the goal is you want to design a revenue optimal truthful mechanism for selling a few different items to a few heterogeneous buyers. So for this audience, I don't think I need to really talk about much about the background of this problem, so let me just go over it quickly. So I have one item, one buyer. That's the simplest case you can have. So what you do is you set this price, which is sometimes called the monopoly reserve price, and that's the optimal auction in this simple case. When you go to a slightly more complicated case, when you have multiple buyers, Meyerson actually provided a very clean solution to this problem. He showed there is a simple, deterministic, and dominant strategy incentive compatible mechanism that optimizes revenue. Okay? Just to quickly remind you the mechanism, so the designer or the auctioneer collects the bids, and for each bid, he's going to apply the virtual value transformation to the bid to get the virtual bid, and then he'll choose an allocation that maximizes the virtual offer and charge the Meyerson payment to make sure it's a truthful auction. Okay. So it's a very simple mechanism, and it gives you the exact optimal revenue. So a big challenge is how you can extend his results to multi-item settings. And so this problem turns out to be harder than it might seem to be. And there has been a lot of work around this problem. So this is just a partial list of the results. But unfortunately, there's no really any general approach. And in fact, the problem is already kind of challenging when you just have two items and one bidder. Okay, so next I want to show you a few examples. Yep.
So people have studied this in economics, like not from computer science, right? But
Yes. So basically, I think up to here, everything is from economists. Yeah. Okay, so I want to show you a few examples where you only have two items and one bidder, and the optimal solution is already kind of complicated, much richer than the one you see for single item. So here you have one additive bidder. You have two items or sell. His additive, meaning his value for both items together, is just V1 plus V2. And his value for the first item is draw uniformly between 1 and 2. Same for the second item. And V1 and V2 are drawn independently. Okay? It's a really simple setting. So sort of a trivial approach to this problem is you can just set a price for each item, okay, and let the buyer take whatever he wants. If you do some calculation, the best way to set the prices will be to price each item at 1. So in that case, both items are sold all the time, and the expected revenue is 2. But that's not the optimal solution in this case. Turns out you can do the following. You can create a grand bundle and sell the bundle at price 3. In that case, you sell the bundle with probably 75%, and your revenue is strictly larger than 2. Okay? So the lesson here is if you want to optimize revenue, sometimes bundling helps. So I want to show you another example, which is very similar, with a slight twist on the value distribution for the second item. Now it's uniform between 1 and 3. Okay? So the unique optimal auction in this case is the following. The auctioneer offers two options to the seller. So the first one is, again, a grand bundle. So you bundle the two items together and ask for $4. The second one, if you look at this carefully, is just half a painting. So this option is a lottery, meaning that if the buyer pays $2.5, he's going to get a first painting for sure, and get the second painting with probably 50%. Okay, and the buyer can take whatever option he likes the best. That's the auction. Okay. Turns out this is the optimal auction in this case, and it's the unique optimal auction. Okay. So that's the revenue. I think the lesson we can learn from this example is even you have very, very simple setting, just 2 items, 1 bidder, you might need to use randomization to get the exact optimal solution. Okay. So I want to show you one more example. So now I'm going from discrete distributions to continuous distributions. So now both V1 and V2 are drawn from 2 beta distributions. So in a result by Daskalakis, Dakopam, and Hamos, they show that the optimal auction in this case, you need to actually offer infinitely many randomized bundles. So each bundle here is randomized. And in fact, not just infinitely many, you need uncountably many. So you cannot even offer this as a menu. Okay. So that's what happens when you go to this continuous distribution.
Only if you don't know.
Only if I don't know. Sorry? If you
Only
don't
if
know.
you're not analyst.
Yeah, so you can write it as a function, I guess. Okay, so through these 3 examples, hopefully I convinced you that just with 2 items and 1 bidder, the structure is already much richer than you have only 1 item. And I think it's fair to say it's quite unlikely to have a simple and closed-form solution if you want to solve this problem in general. So I see 3 possible ways to proceed. One is to look at special cases. Usually this involves making assumptions on the distributions. So many people have applied this approach to the problem, including myself. So this paper is actually what I did while I was an intern here a few years back. So I'm not going to talk about this result. Another one is you can actually think of this as a computational problem and just ask for an algorithmic solution. And with Costas and Matt, we managed to show there is a polynomial time algorithm that actually finds you the revenue optimum of the item auctions. Okay. There's another one, which is basically I'm going to insist to have very simple auctions. But just through the 3 examples, you've already seen that if you want really simple solutions, for example, deterministic ones, you cannot get optimal one. Yeah, sorry.
So second bullet, previously you showed that optimal options can be like infinitely many. So what do you mean by there are polynomial time?
Right. So polynomial time, if your type space is discrete, if you have continuous, you can discretize that. You get 1 minus epsilon, basically.
Okay, so
Yeah. So you do lose a little bit, but you can basically, by paying more time, you can get a smaller answer. Yeah. Okay. So the last one is I want to actually use simple auctions, but I have to sacrifice some optimality. And the question is, of course, how much I have to sacrifice optimality. Okay. So that will be the focus of this talk. Okay, so let me be a little bit more specific about what I mean by simple mechanisms. So to remind you, in the single item setting, Meyerson's auction is pretty simple. It's deterministic, it's DSIC, and it's exactly optimal. As we have seen in the 3 examples, if you just go to 2 item settings, the optimal mechanism may need to be randomized. It might use very complex allocation rule. And very often, it's only Bayesian incentive compatible, which is a weaker solution concept. Dominant strategy incentive compatible means no matter what other people are doing, it's a dominant strategy to report your true value. Bayesian incentive compatible means if you assume everyone else is reporting according to their true value, it's an equilibrium for you to report your true value. Okay, so it's a weaker concept. So the challenge here is, can we just use mechanisms like the ones above, like simple, deterministic, and DSIC, to approximate the optimal revenue you can obtain using any complex, randomized, and big mechanism? Okay. So in the example, we already see that randomized mechanisms are strictly more powerful than deterministic ones. And recently, in a paper by Yao, he actually showed that big is also strictly stronger than DSIC. So the optimal big revenue is strictly larger than optimal DSIC revenue, even when you only have 2 items and 2 bidders. Okay? So I'm really restricting myself to a strictly less powerful class of mechanisms. Now the question is it possible for me to get a good approximation? So there has been some breakthroughs on this front, actually. When bidders are additive, so in a recent paper by Yao, he showed that you can either sell the items separately, so you sell each item using Meyerson's auction, or you can run the VCG mechanism with entry fee. The better of the two gives you constant fraction of the optimal revenue. I'm not going to tell you exactly what these mechanisms are. I'm just going to explain what the mechanisms look like when you only have one bidder. If you only have one bidder, so you can either just sell the item separately, meaning you post a price for each item, and the buyer can take whatever item he wants. That's mechanism one. The second mechanism is you just offer a grand bundle. Okay? And the better of the two gives you 1/6 of the optimal revenue. Okay. So the main challenge for obtaining these approximation results is basically it's very difficult to come up with a good upper bound for the optimal revenue. There's a trivial upper bound we can use, which is the social welfare, because you can never charge a buyer more than his value. Okay? So social welfare is an upper bound of your revenue, but unfortunately, this could be unboundedly bad. Okay? So if you use that upper bound, there's no way you can get a constant factor approximation. And the main technique that enabled this line of work is called quartile decomposition, which is a probabilistic tool that gives you an upper bound for the optimal revenue in the additive case. Okay. And this technique has been also applied elsewhere. So these are just a few examples of papers that also use this technique. So that's for additive buyers. When bidders are unit demand, meaning only one item, there's also a simple mechanism that gives you a constant factor approximation of the optimal revenue. And again, I'm just going to tell you what the mechanism looks like when you have only one bidder. So the mechanism is you post a price for each item, and the buyer just takes whatever he likes the best. Okay? So that's the mechanism, and that gives you a factor 4 approximation of the optimal revenue. So again, the challenge is how you can provide a good upper bound for the optimal revenue. It turns out the technique they use is not the quartile decomposition, and it's not clear whether you can use quartile decomposition to get an upper bound in this case. What they use is the following technique. They can upper bound the revenue by the optimal revenue in a related single-dimensional setting. Okay? You have an original setting. You create a single-dimensional setting. The revenue in the original setting is upper bounded by the optimal revenue in the single-dimensional setting. Okay? And the single-dimensional setting is called a copy setting. And because it's single-dimensional, you can use Meyerson's theory to actually compute the optimal revenue in it. Okay? So that gives you an upper bound. And also has been successfully used in other works. So I think the takeaway from these two lines of results is that we actually have quite strong tools to study this problem. But these tools are kind of tailored for specialized settings. For example, the quartile decomposition is unclear if you can use that to solve the unit demand case, or you can use the copy setting techniques to solve the additive case. Okay? And it's also unclear whether you can generalize these techniques to handle broader settings. Okay, so with Nikhil and Matt Weinberg last year, we provide a principal approach for designing simple mechanisms using duality theory. In fact, we identified this one single dual. If you apply this single dual to the single item setting, you get back Meyerson's result. If you apply this dual to unit demand setting, you can rederive and actually improve the upper bounds you can obtain using the copy setting technique. If you apply that to additive setting, you can also rederive and improve the upper bounds you get via the quartile decomposition. Really, just this one dual solution allows you to produce all these results. Okay? And in fact, by analyzing our new upper bound, we managed to improve the constant ratios. Okay? For additive, improved from 69 to 8. For unit demand, we improved from 33 to 24. So in the beginning, when Nikhil, Matt, and I started talking about this problem, our goal was to actually come up with a general framework that allows us to extend these simple mechanisms to broader settings. Rederiving and improving the previous results was just first step. And our hope is really this framework allows you to study other valuations, more general valuations. With my student Mingfei, we made some progress on that. And indeed, we can show not just the framework works, you can essentially use the same dual to get upper bounds that allows you to prove all these new approximation results. Okay? So I said essential because it still requires some substantial work to extend the framework to accommodate these more general valuations. By the end of the day, the dual we use to obtain these results shares the same intuition. So let me walk you through the results. So I'll tell you what the mechanism looks like in the next slide. So let me just first state the results. So if you have only one buyer, for matrix rank, we improved the ratio from 33 to 11. So the same ratio holds for a slightly more general class called constraint additive. For XO's valuation, we get 40. XOS is a superclass of some modular valuations. And the 40 also holds for a more general valuation class for a cost of additive, which improves the 300 ratio. That's the state of our result for this case. For multiple buyers, the broadest case we have a constant factor approximation is matrix rank functions. And we improve the ratio to 70. And so same ratio holds for constraint additive as well. And we also have a constant factor approximation for XOS. If you go to subadditive valuations, the ratio becomes log n. Okay. So that's the statement of the result. So now let me show you what is the mechanism. So the mechanism is quite simple. So for each buyer I, I'm going to decide a price vector, pi. So pij will essentially be the price I'm going to charge for buyer I to purchase item j. Okay? So I decide the prices upfront. So these only depends on the distributions. Now the buyers arrive in some arbitrary order, okay? Sequentially, but arbitrary order. Not random order, arbitrary. I'm going to show buyer I the available items and the prices. Next, I ask the buyer to pay some entry fee EI. This entry fee might depend on what are the items are still available, okay? And the identity of the buyer. If the buyer agrees, she can enter the mechanism and take any subset SI and just pay the corresponding prices, okay? That's a mechanism.
This is in addition to the entry fee.
That's addition to the entry fee, yes. So first, it's not hard to see this is actually a DSIC mechanism because it's very straightforward for you to decide whether you want to pay the entry fee or not. You just compute the largest surplus you could get if you enter the mechanism. If that's higher than the entry fee, you accept the entry fee. Otherwise, you turn it down. Okay? So that's very easy to decide, and it's DSIC mechanism. Okay, and the prices are determined upfront. I'm not even updating the price adaptively. Okay. So this is already a very simple class of mechanisms. In DY, actually only use two special cases of this mechanism. Okay. The first one is called sequential posted price mechanism. So in that one, I don't have entry fee, okay? Just the prices, item prices, okay? But the prices might depend on the identity of the buyer. The second one called anonymous posted price with entry fee. So here, there's no personalized price, okay? For every item, there's a single price. So Pij equals Pkj, okay? But I might still need to charge entry fee in this case, okay? So the claim is the better of these two mechanisms gives you the approximation ratios I showed you in the previous slide.
Entry fee could be personalized.
Entry fee could be personalized. And
May
I think
also
you
depend on
the available items. The available items, yes.
But isn't it same then? Like if entry fee is personalized and the prices are same, then you could think no.
No.
So in a way, this mechanism itself is not constructed from the dual.
It's not.
But it's inspired or something.
Yeah, so you cannot really just read the dual and produce this. Yeah. Of course, like the dual has some particular format, so you can guess what it is, but this doesn't directly tell you what the mechanism is.
want some guidance.
it does give you some guidance.
I mean, do you use it to compute the prices or
No.
not even that?
Not even that, really just gets the format.
Okay. You use the prices to compute the dual.
Yeah.
Maybe something has to go
Use a
one way or the other.
distribution to compute both of them.
Yeah. Sure. Yeah, so basically it's like if you look at the upper bound, you see some terms of the particular format, basically you guess what the mechanism is. From that, of course, you compute the prices. Yeah. Okay, so that's the statement of the result. So for the rest of the talk, I want to show you the duality theory. And I will use a single additive bidder as the running example and show you the dual and what I will show you the dual and also show you, the primal I will show you for sure. I will show you the framework and also the particular dual I'm going to use. Okay, so that's the claim. And so, I mean, although this is a special case, I think it contains basically the idea behind the dual. And so it's possible to generalize this to multi-bidders, more general valuations. It's non-trivial, but it's doable. Okay, but I'm just going to show this case.
By the way, you're assuming just that you're assuming product distributions.
I'm assuming product distributions. And
that's
for the
your
previous
product
results,
also.
everything, all the results, I'm assuming product distributions. Yes, everything's for independent items.
But not necessarily independent bidders, or
Bidders are always.
I don't think you need independent bidders, but if the bidders are correlated, you cannot compare to the optimal big revenue. You can only compare to the optimal DSIG revenue. So that's a claim, I think.
complicated.
Yeah. Basically, the primal, you need to change the primal.
Yeah, I mean, we don't even have
Often
bounds
it's-
for that.
Yeah.
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 Single item.
Worst case is just welfare. So
Yeah,
there's
for
no way to
BIC.
compare.
For DSIC, we do.
For DSIG, we do. Okay, so let me first fix the notations. So bidder's valuations, V, is drawn from some known distribution, D. And capital V is the support of the distribution. Bidder's additive and has quasi-linear utility. And I'm going to make this technical assumption that all the items are independent, which was used in all the previous works. Okay, I want to optimize the revenue. And as you said, I'll also show you the primal. Which is kind of straightforward LP. So I'm going to write the revenue maximization LP for one bidder. So here are the variables. So X-ray of V is the probability for receiving item J if you report V. P of V is the corresponding price. So here are the constraints. So the first one is the truthfulness constraint. The left-hand side is what you will get if you report your true value V. That's your utility. Right-hand side is your true value is V, but your misreport say your value is V prime. That's your expected utility. Truthfulness constraint just that the left-hand side is greater or equal to the right-hand side. So I also have some feasibility constraints. In this case, it's kind of trivial. It really just says for any valuation V, for every item J, I want X of V to be really a probability. So between 0 and 1. Okay? So that's a trivial feasibility constraint. The objective is the expected revenue. So F of V is just the probability your valuation is V. Okay? So that's the expected revenue. So that's the primal.
And you have IR as well.
I have IR. I'm not showing it here. The way to think of IR constraint is imagine you have an extra type says, I'm not participating in the auction. So IR just says reporting your true value is better than that. Okay, so you can absorb that in the truthfulness constraint.
So, but this is like a continuous relaxation, right? Because you did not as the distribution can be like continuous distribution.
So for now, let's just think about discrete distribution. For continuous, you can throw an epsilon net, things like that. I'm doing constant factor approximation. I mean, I don't care to lose another epsilon. Of course, I think you can write the continuous LP and do a duality.
I think you're using only for analysis.
Yeah,
So
yeah, you can also do that too.
Can also do
Yeah, I think you can also do that too.
yeah, fine.
Okay, so that's the primal. So let me show you the dual. So I'm going to Lagrangeify the truthness constraint and obtain a partial Lagrangian. That will be the dual. So the dual, I try to minimize over all multipliers, maximizing over all x that's feasible and all payments of this L function. Okay. The L functions, really, this is the objective function plus the Lagrangian multiplier times the corresponding constraint. Okay? So lambda v prime is the multiplier for this particular constraint. If your true value is v, misreporting v prime is not helping you. Okay? So that's the multiplier for that particular constraint. So I'm just Lagrangeifying all the truthness constraints here. So the next step, I want to rearrange the terms. So this might look pretty heavy, but really what I'm doing is I'm separating the payments. So the red term is everything that's related to the payments. The black term here is everything relates to the allocation. Okay? So I'm separating the two. So let's just look at this red term here. Notice that for payments, I have no constraint. So it's unrestricted. So if I want the dual to have finite value, it better be the case for any v, the coefficient for PV is 0. Otherwise, I can either choose this to plus infinity or minus infinity to get a plus infinity upper bound, okay? A plus infinity dual value. So that is an upper bound for my optimal revenue, but it's a useless one, okay? So for me to obtain anything meaningful, I better restrict myself to only consider lambdas that makes this 0 for all v. Okay? So that's just a simple observation from the dual.
The IR constraint doesn't impose a limit on P of V? I mean,
No.
I know it's kind of buried in here, but
The IR constraint,
I mean,
it does, but I already Lagrangified those constraints. So now the P really has no constraint. So I'm only leaving these constraints there.
So you're leaving distribution that x of v
Well-
is a distribution constraint, right? That's the only thing you're leaving.
Yes, that's the only constraint I'm leaving.
Yeah.
I'm only leaving constraints on X.
in particular, P for this special type is
0.
Zero.
That's the only one I have.
okay.
That's the only one I have. For the other PV, I don't have anything.
Okay.
Yeah, that's the only thing I have.
Okay.
So I think the next slide you'll see the IR constraint actually correspond to something special because I leave that constraint there. Yeah. So this is just one simple observation about the dual. So for every valuation V in the support, this should sum up to be 0. If you look at this for a little bit, you realize this is very similar to a flow conservation condition. And it does correspond to some flow on the following graph. Okay? So in the graph, you have a super source S. You have a super sink. I put empty set there. So that's basically the type that corresponds to IR. Okay? I'll explain a bit more later. And I have a node for every valuation V in the support. F of V is the amount of flow that goes from the source to node V. So that's fixed. That you cannot change. Okay? So these are the black edges. Then lambda V prime correspond to the flow that's from node V to V prime. Okay? So this is this you can choose. So in particular, V prime can be the sink. Okay? So really think of sink as the type that corresponds to IR. And lambda V, the empty set, is the multiplier for the IR constraint for valuation V. It really says if your true value is V, you don't want to report this empty set type.
So we don't get this flow conservation constraint for the empty set because we set that price
Because
to
that
0.
price is already
That price is
zero.
0,
So
exactly.
it's not a
Right,
free
okay.
variable.
Exactly.
Right.
So that's why we don't get flow conservation. And then now you can just think of it as a sink.
Yes.
Good. Okay.
Can you please write the IR constraint on board? I mean,
Say it again.
so what's the
IR constraint is just when V prime is 0.
Yeah, so basically
It's
says
the
X empty set is 0, P and empty set is 0.
Okay, so
So our constraint just says if your true type is V minus PV is greater or equal to V times X empty set minus P empty set. Right? These are both 0, so you get 0. So that's IR constraint.
Right.
So you can absorb that as the truthfulness constraint.
Strictly speaking, you don't have to impose X empty set to 0, but it will happen that way. You could
I
give something
don't
for
have
free,
to.
but you will never want to.
So you're saying I don't have to post this for 0. Because
You don't have to
maximize-
make the X.
I don't have to make X to be 0. Then it's not exactly the constraint, I think. That's not
You
exactly
could
IR.
give something for free,
yeah, so that's
but it'll happen.
Doesn't-
No, but you'll never want to give something for free.
Okay.
Optimum will never do it.
Yeah, okay. So let me continue with this. So this is how you interpret this lambda as a flow. This just says for every node except the super sink, you have flow conservation. Okay. So this simple observation allows us to further simplify the dual. So now I'm only looking at all lambdas that corresponds to a flow. So in that case, all the coefficients for the payments are 0. So I can ignore the payments, only look at the allocations. And also I can simplify the L function just because the fact that lambda is a flow. I'm not going to show you the derivation, but you can do that. Okay? So the L function now looks like the following. So x of v is an m-dimensional vector. What's inside the parenthesis is also an m-dimensional vector. M is number of items. So what I want you to think about this term inside the parenthesis is the virtual valuation of v. So the j's coordinate is virtual valuation for item j, which looks like the following. Okay? So it depends on your choice of the dual. So this is just one definition. I can make whatever definition I want. But under this definition, the L function has some interesting interpretation. Okay? So I can rewrite the L function as this. Okay? If I ignore the f of v, just look at this sum. So I'm summing over all j, the probability I'm receiving item j times the virtual value for receiving item j. So that's my virtual welfare. Now I multiply the probability, my valuation is v, sum over all v. That's just my expected virtual welfare. Okay, with respect to this particular function. So now what does it mean for my dual? So the dual, I'm picking one particular lambda. Now I choose an x that maximizes this L function. So I'm picking an allocation that maximizes the virtual welfare. Okay, so that's the dual. Okay. So just by weak duality, this already tells us if you look at the optimal primal, which is the optimal revenue, it's upper bounded by the optimal virtual welfare with respect to any flow lambda. Okay, so that's weak duality. Strong duality tells you if you pick the optimal lambda, okay, lambda star, the optimal virtual welfare will be the same as the optimal revenue. Okay, that's strong duality. So it turns out you can use strong duality to rederive Meyerson's result. So if you apply the optimal dual in the single item setting, you get back exactly Meyerson's virtual value. So for us, it's more useful to use weak duality. So next I want...
some particular choice of flow.
For some particular choice, that's what I'm going to talk about next.
For Meyerson, for something else.
For
But also
Meyerson?
for Meyerson, you had this
The
lambda thing.
The optimal flow.
Dual, which is optimal flow, will give you
The Meyerson
Meyerson's
virtual value.
I'm
The
sorry.
optimal-
Okay,
the
okay,
optimal
the
flow.
optimal
The
flow.
optimal flow.
The optimal flow, which is determined by lambda.
Yes.
Okay.
That will give you Meyerson.
Yeah, sure.
Okay.
But you're not telling us what it is. I mean, well, we know what it is.
Oh, we know what it
what
is.
the result is.
Yeah.
But the thinking about it as a flow is a little different from.
Yeah, so I think maybe later you see a little bit what the flow looks like there.
Okay.
Yeah, once somebody tells you this, then it's kind of easy to guess what the flow should be. You can reverse engineer it. Because you know what
you
the,
know what the answer is supposed to be.
you know what the virtual value is.
Okay, so in the next few slides, I'm going to show you how you can actually set the dual in some canonical way, and that will give you some tight upper bounds for the optimal revenue. Okay, so and that upper bound will be the one that you use to get all these approximation ratios.
Okay.
Approximate. I will pay approximately tight. Yes, yes. Okay, so for simplicity, I'm going to assume the typeset is on some integer lattice. Okay, so say h is some big integer. Okay, so if you want, you can even think of the case like m just equals 2. Okay, you only have 2 items. So first, I'm going to divide the bidder's typeset into m regions. Region Rj will contain all types that have the j's item as the favorite item. Okay, so let's just look at this example. So the blue region is R1. So every type there has V1 greater than V2. So item 1 is the favorite item. That's why it's R1. For the yellow region, every type prefers item 2 to item 1. Okay, so that's how I divide the type set. So the flow, the particular flow we're going to use is the following. First, there's no cross-region flow. Okay, so you never have a flow that has the head in R1 and the tail in R2. Okay, all flows remain in the same region. Okay. And 2, for any V prime and V in Rj, there's a flow between them only if these 2 types only differ and differ in the j's coordinate. Okay, the only difference they have is at the favorite item. Okay, so what it means in this particular example, so let's pick j to be 1. Okay, so if v prime and v are in R1, there's a flow between them only if they have the same value for the second item. Okay, so that means the flow always goes horizontally. And also, I want vj prime to be vj plus 1. That means you're really just pushing the flow to the one on your left. Okay, in R1. In R2, you're pushing directly down. Okay, so in R2, always vertically. In R1, it's always horizontally. Okay, so that's the flow.
And then your source is going to send flow
to every
the
node.
edges.
To every node.
To every node?
To every node. The source will send flow to every node. So it's a supply. F of v. That's just the probability for that node.
Oh, sorry.
So let me go back to that particular.
Every node has a supply of f of v.
Okay, so now just on this picture, let's imagine that that's a V2, fix the V1 value and you have some V2 and the other one is minus 1.
Okay.
V2 minus 1.
Yeah.
So you had only flow going down.
Yes.
You had no flow going up.
No, right.
You had the F of V, you always had the F of V.
The black ones are fixed.
Okay.
There's always there. Okay. And
Okay, so once you've specified that, you're just pushing the flow through and you know what the lambdas are.
Yes.
Because it's all going in one direction.
Right.
There's no cycles. Anyway.
There's no cycles. For this simple ones, there's no
except
cycles.
You have the freedom with this
So
one edge
and for
going to-
every so let me say this. So you keep pushing the flows till you hit basically the 45-degree line. When you hit there, you dump the flow to the sink. For the
So
other,
all the other ones are
the
going
other
to-
ones is really just pushing to the one next to you.
No, but there is such an edge to the empty from every node.
Yeah,
that
but
you
it's
say
zero. It's zero.
Except,
Except
on
at the
Except on
45
the
degree.
diagonal,
Yeah,
you cut
except the
off forward
diagonal
and
one.
send it to
Yeah,
us.
except the diagonal one.
So how did you know to do this, or where does this come from? Why?
So I'll explain 2 properties. Hopefully that gives some intuition why this is a good thing to do.
Okay.
So this is very simple dual, but it has 2 nice properties. The first one is if V is in Rj, then V's virtue value for any non-favorite item is just the value. Okay, so let's look at the formula here. Suppose J is 1. Suppose V is in R1, J is 2. Okay, so this says virtue value for the second item is just V2. Okay, why is that? So you already get V2 here. Okay, so basically this term is 0. Why? Because whenever the lambda is non-zero, V2 prime is the same as V2 because you're only getting horizontal flows. Okay, so this product is always 0. So I'm subtracting 0, so I get back V2. Okay, so that's why for any non-favorable item it's just value. A somewhat more surprising thing is if you look at the virtue value for the favorite item, you get Meyerson's virtue value function for that particular item. So phi j is just with respect to the distribution for the jth item. Okay. So let me show you basically you can, how you can prove this. It's really just by computation, by the definition, follows from our definition. So suppose you're in Rj, so all the flows just go directly down on j's coordinate. Okay. Think of this as j is what? J is 2. So it's really vertically going down. And for Vj, it's not hard to compute the amount of flow here. It's really just the total amount of flow coming from source to all nodes above it. Okay. So that's just this probability. So you multiply the probability that the other items has value v minus j, and the probability for the jth item, the value is above Vj. Okay. That's how much flow you're receiving. And if you put that into our virtue valuation function, that's what you will get. And that's Meyerson's virtue value function. Okay. So going back to your questions, like what's the flow for Meyerson? This is the flow. Okay. When you're regular, this is right flow. If it's non-regular, you need to do some ironing, which I'm not going to talk about here. But that's basically the flow. Okay.
Actually, where does regularity? So this gives you an upper bound for non-regular as well.
This will give you an upper bound for non-regular as well. Regularity just comes from whether this is monotone or not.
Right.
Yeah.
Oh, well, actually, you haven't translated this into an allocation rule yet.
No, yeah.
So I'm just wondering, because this was a well-defined flow, you've defined everything,
Yeah,
it's great.
yeah.
It didn't, nothing here so far depended on regularity.
No,
I mean,
right.
it was only when
No,
you go to an
no,
allocation rule that
no,
it's going to be a
exactly.
problem.
That's right. So this is always a virtue value function. When it's non-regular, you need to do ironing.
Right.
That's what I'm saying. Okay.
You get a better bound by doing that.
Yeah. So this is not going to be a tight upper bound. Okay. So hopefully this gives you some intuition why we picked this flow. So any flow lambda gives you an upper bound. In particular, you can pick the empty one. Empty one means you receive some flow from the source, you just dump it to the sink. Okay. So all lambdas here are 0. So in that case, your virtue valuation is just your valuation. Okay. So your upper bound was just optimal social welfare. Okay. It's an upper bound, but it's a useless one. So what we try to do here is going to look at the terms that contribute the most to the social welfare. And in this case, this is your favorite item. Your favorite item contributes the most to the social welfare. So try to replace that with something else. And using this particular flow, you can replace that with the Meyerson virtue value. And this is useful. Just imagine when you have only one item, one bidder. Social welfare in that case is just a value. That's the upper bound for your optimal revenue, but it's unbounded. And replacing with virtue value, you actually get the tight upper bound. Okay, so you can improve basically unbounded ratio. And turns out it also works for multi-item as well. So here, this corollary is just combining the two properties. Says if you're the first, if J is the favorite item, if J is not the favorite item, the virtue value is just Vj. If it is the favorite item, it's Meyerson's virtue value. So I can plug this into the out function and get an upper bound. Okay. So this is an upper bound I get from this particular flow. So really, the way to look at this is I'm replacing the value for the favorite item with Meyerson's virtue value. So the theorem, one theorem is you can actually show selling separately or grand bundling achieves 1/6 of this particular upper bound. Okay, so using this upper bound, you can get the 6-vector approximation that's shown by et al. Okay. So far I've been talking about additive settings. Turns out you can do the same flow in unit demand settings. You will get exactly the same upper bound. And you can use this upper bound to prove poster price mechanism gives you 1/4 of the optimal revenue. Okay, same upper bound.
Okay, can you say just a few words about how you get the let's say the bye-bye
Okay,
from this? Just the idea roughly of the rest of the
The idea is, well, you just break this upper bound into a bunch of different terms.
Okay.
One particular I can say is if you just look at what the virtual value, Myers and virtual value contributes, that's minus separately.
Okay, yeah. So how do you get the grand bundle?
From here, basically you can break that into two terms. One is selling separately, the other is grand bundling. This term you need to break up too. So basically for VJ, that's not the favorite, but have relative high value. Those you can attract with selling separately.
Okay, so grand bundling is what we know from a bipedal. That's when you're getting social welfare.
Yes,
basically.
yes.
So that corresponds,
Right.
in that case,
Right.
to social welfare.
Right, exactly.
So,
For this one, basically you break it into two cases. You do something similar to quartile decomposition. You say, if this VJ has high value, it's in the tail, I'm going to bound it with selling separately. If this VJ has low value, so it's in the core, I'm just going to take it as the social welfare. Okay, I'm going to dump this indicator function, just look at the social welfare. You can bound that with bundling.
okay, so what you do is you show basically that this particular mechanism basically gets a constant factor of this
Yeah.
upper bound.
Yes,
Exactly,
yes,
in that
yes,
case, by
yes.
breaking it up in a line. Okay.
Yes.
I'm just saying again what you just said. So.
So you do something similar to quartile, but now it's just, if you expanded it some kind of integral or whatever, right, and then just break it up into two terms, one corresponds to the core, one corresponds to the So you don't have to prove the quartile decomposition is upper bound on the optimal revenue. You don't have to do that. So you just get it for
Yeah.
free. It's just you have these terms. Okay, let's break it up. This
Yeah.
Yeah.
Okay.
It's just
Yeah.
simple algebra.
Yeah.
Okay.
And quartile is really just some thresholding. Yeah. Okay, so you can use essentially the same upper bound to get all these results. So I don't know if I can say more about this.
I mean, that's pretty remarkable, actually. Now that you're going to this far,
Yeah.
because this upper bound is, I want to say, like, once you've thought of this whole approach, it's sort of might be the first thing you would try, right?
Yeah.
I mean, it's sort of the simplest way to get the flow and to have it match up to Meyerson and all these other things. I mean, actually, I would like to hear more about how you thought about it when you were coming up with it.
So actually, there's this other LP where you write the utility variables, and you have the dual there. So first thought about it there. There actually, this dual is very natural, and then translate it into this and transfer it.
Yeah, so I mean, I was looking at this partial Lagrangian, and the first dual actually I came up with is not this. I was trying to get Yao's upper bound, or like directly the quartile decomposition. That corresponds to something more complicated, I think. Not exactly this. So you have to do something more complicated, not just like going one direction. I think you need to do, if your value is really high, you need to do both directions, I think. It's a more complicated flow. But then it turns out if you look at this much simpler flow, you actually get the same ratio. Yeah. So, all right. So I haven't told you how you can generalize this to multi-buyers. There you have to do something more complicated. Basically, you have to pick some thresholds. So basically, when you have multiple buyers, you have to define what do you mean by the favorite item. So you're not comparing just by face value. You need to set some thresholds for every buyer, every item. Now you're asking, if you're going to buy the item with this price, which one is your favorite item? So you're looking at the surplus. And basically, the threshold is where all the technicality goes in. You have to pick the right threshold to prove anything. So it's more complicated than this, but it's essentially you're separating the typeset into m different regions and looking at the favorite item. That's basically how you do it. Yeah. Okay, so.
So, are you going to describe the mechanism?
For this?
Like, I mean, the more details about the, like, Sabre XOS.
The mechanism?
Well, okay, you described it in general. You said this either entry fee or posted prices.
Oh, yeah, sure. I can say a bit more. So I guess like the only thing I haven't told you is what the entry fee is. I'll say, okay. I also didn't say that what's the price. That might be a bit harder to say. Actually, I mean, you probably will see tomorrow, which I'm going to do something.
Actually, I can guess already from what you're talking about.
Yeah, so because I'm talking about...
the entry fee, I have no guess.
Okay, the entry fee is, so you look at the prices, you have all the available items. So now I can compute what's your expected utility if you go into the mechanism without paying the entry fee, okay? Take the median of that.
Median?
Median.
Okay.
Take the median of that, that's your entry fee.
Okay.
So that's how you do it.
And why do you need that?
Because of concentration. I need the concentration part to get the core. Basically, I need the core part.
You need to expect some more.
So just posted price, you're basically just getting the tail. You want to get the core. That's why you want the entry fee.
Wow, nice.
Yeah. So.
Actually, that applies for a single bidder, doesn't it?
Yeah, it works for
I mean,
it works for XOS. So it works.
No, I mean, but so you do that in the XOS say for a single
for
bidder.
everything. I did that. Okay, for XOS single bidder, you don't even need the posted prices. Just grand bundling. So for XOS one bidder, you can do either just selling separately and grand bundling, and that gives you 40.
Okay.
Yeah, you need the posted price just because you have multiple buyers.
I don't really
What about
understand.
sub-additive?
It's about the same. So the mechanism for single buyer is the same as in their paper, like Avia and Matt's paper. It's just we improved the ratio. Yeah. Yeah, selling separately or grand bundling. Yeah, that's it. Yeah. So for multi-buyers, I need the new mechanism. Yeah. Thumbs up, I guess. Okay. So.
Also for just for additive,
Yeah.
we had VCG.
We have VCG, yes.
But now you're saying you don't need to do VCG?
I'm saying I don't need to do VCG. Actually, I don't know how to prove VCG will work. I don't know whether VCG works or not. I actually don't know about that.
Wait, isn't that what we had?
No, for additive, yes. I'm saying like for more general, we don't know.
Right.
And we were stuck for like K-demand trying to do VCG for K-demand for quite a while.
Right.
Yeah, and now I still don't know.
And you're saying you don't have to do VCG.
You don't have to do
this
VCG.
sequence.
Yes.
So that would also work for additive,
They will also work for additive.
but
yes.
you get a worse bound or.
Yeah, so maybe for additive you can improve this slightly. I don't think you can get 8. Yeah. Yeah. I mean, in this analysis, you got like 5-6 parameters you have to tune. So I don't know what's the best ratio, but like I optimize a little bit, so this is what I get.
And what's constraint additive?
Yeah, so you have a downward constraint, feasibility constraint. So like matrix rank is you have a matrix feasibility constraint. This is just general downward close. Your additive is subject to that. So basically, this is a place you cannot use contention resolution to do the bounding. Like contention resolution works for matrix rank, works for like matching and like intersections of that. So that's what Shuchi and Ben did in their paper. But that doesn't work for general downward close. So just to get this, you already need the new mechanism and a new analysis, basically. Yeah. I'm not getting a constant here. Is basically here I'm using things like supporting prices. I mean, you probably already guessed.
Well, what do you mean by supporting?
Okay, so for XOS, you have this thing called supporting price, meaning for if you take any set S, you can take the maximum additive function there.
Oh, yeah.
So you can. That's the property for XOS. For a subadditive, you don't have that. So you lose log m there. So
required?
So I don't have a lower bound for that yet. It's also not clear to me how you can prove a lower bound for like simple mechanism. I guess you can go say, okay, there's no desig mechanism that gives you something better than this. But if you say simple, I don't know what it means actually.
But you can say,
There
okay,
are
even
You can prove to say.
of the form you showed.
Yeah, that's already cool, I think.
I mean,
it's unclear.
you can
if
have
do.
optimal mechanisms for these, right?
Yeah.
Because that's just a convex program.
Say it again? Oh, yeah. You can definitely write a program for that. Yeah. So.
Yeah. So they already have a computational result.
Yeah.
So
the
you
question,
have-
okay, so then lower bound doesn't make sense.
Yeah, I mean, you can prove, like, say maybe there's no desig mechanism gives you better than log n of the optimal big revenue.
I
So you
see,
can prove
because
that.
The optimal is still in Bayesian.
Yeah, like all these are comparing to the optimal Bayesian instead of compatible revenue. Although the
Computational
mechanisms are
result
desig.
is also not a deterministic mechanism. It will offer lotteries.
Yeah, you have to do randomization, you have to do all these things.
Right? Yeah.
Or you can prove maybe the deterministic one doesn't give you better than this.
Yeah, so that's true.
And also, I'm not sure this is the right answer. Maybe it's constant. So it's just like the techniques I have so far only gets me log n. It's number 5. Okay. So I'll just show you the last slide. I'm not going to say anything. So that's it. Thank you.
Yes, do you have any questions?
Yeah.
Well, also I get to talk to him tomorrow, so
He's around here today.
yeah, today I can't.
Tomorrow.
It's really cool. It's really nice. I mean, oh my God, everything's getting so simple. I mean, not the proofs, but the
The
mechanisms.
mechanism is.
I mean, to go so far, I mean, to go all the way to XOS and get like a constant factor approximation was fantastic. I mean,
Yeah.
it's, you know,
They couldn't even, like
I
a couple
mean,
of years ago,
this
even
was-
two
this was like
additive
something-
items, no, we didn't have any idea how, what
I
was
mean,
going
my
on.
God, this is so, I mean, the mechanism is so
Yeah.
simple. That's what I love about it.
Yeah.
It's,
Yeah.
And I like the fact that the duel is so simple. I didn't really understand how it worked before. So, just tell you the truth.
Yeah.
Really read the paper.
That's it. Yeah.
But
Yeah.
actually,
Yeah, it's
I
actually
mean,
not so complicated. Yeah.
it's, I mean, I only understood it in that special case. Well, actually, I guess it's all,
Yeah.
Yeah.
So
I mean, I
For-
can really,
Yeah.
for additive, we actually need to do something more complicated in our stock paper. We're taking a distribution of flows. So this is one flow
So this is
What,
for single
you
bidder,
need that?
right? So
for
when-
multiple buyers.
For multiple
For
buyers.
multiple buyers.
okay.
You
Yeah.
need to take flows like this and take their convex combination.
Yeah, we take a distribution of
Yeah,
flows.
and then
Those are
tomorrow you
distributions.
might have to explain that to me.
Yeah.
But,
I think now you don't. So the new proof, like I'm not taking distribution for the XOS result.
Oh, really?
Yeah, I'm not taking distribution. But like you have to pick basically the threshold more carefully. So it's not something like corresponding to a VCG.
Incorporating the distribution already into the way you're picking.
Yeah, I mean also like it's not clear why we need the distribution. It's sort of like a probabilistic proof. So maybe if you pick the right threshold, it just works. So,
really cool.